Hello everyone, I'm Jiao from Shanghai Jiao University. It's my honor to stand here and introduce our work, GAN-driven study distance supervision for relation extraction. My presentation is divided into 4 parts. Firstly, I will provide a quick review of relation extraction and distance supervision. I will focus on one kind of wrong labeling problem called false negative instances. After that, I will introduce our method to solve this problem. We construct and curate data set by filtering credible instances and propose a 3-player min-max scheme to generate proper relation representations for unlabeled instances. Next, I will show some experimental results to prove the effectiveness of our method. At last, I will conclude this work. Our work is also about the task relation extraction. Relation extraction is a classic task in natural language processing. It takes to extract the predefined relations between a pair of entities in a sentence. For example, in the sentence, Steve Jobs was chairman and co-founder of Apple Inc. We can extract the relation founder between Steve Jobs and Apple Inc. To overcome the limitation of manual labeling, distance supervision was proposed. It assumes that if two entities have a non-relation in a knowledge base, all sentences that mention the two entities will probably express the same relation. With this assumption, much bigger data sets can be constructed and used in relation extraction. Obviously, this assumption is too strong. For example, the sentence Steve Jobs resigned as the CEO of Apple Inc. in 2011 will be labeled to have the relation founder in the dataset because it has the entities Steve Jobs and Apple Inc. Therefore, most recent works focus on this kind of wrong labeling problem of false positive instances caused by this assumption. However, in this work, we address another kind of wrong labeling problem, which is caused by false negative instances. Those instances may have relations in reality, but are misclassified as non-relation in the database. This phenomenon is caused by the incompleteness of existing knowledge bases. For example, according to previous work, over 70% of people included in freebase have no date of birth, so sentences containing these entity pairs are likely to be misclassified as non-relation. Here we show some false negative instances in the table. They are all labeled as non-relation in the automatic data set, but all have their own relation. False negative instances will bring many problems for distance supervised relation extraction. It will not only mislead the training method to unreliable convergence, but also makes the measurement criteria inaccurate in the testing process. In this table, we compare the precision of automatic and manual evaluation method for top N predictions by the model P10+AT. There's a huge gap between automatic evaluation and manual evaluation, which we think is mainly caused by the false negative instances. To solve this problem, we firstly construct an accurate data set. We make the assumption that if one entity is relevant to another entity, its name is totally mentioned in the description of the other entity. This mention may be bidirectional. For example, Steve Jobs and Apple Inc. both mention each other in their Wikipedia pages. And this mention can also be one direction, such as Steve Jobs and the United States. To verify the assumption, we count the number of all the positive instances whose entity descriptions mention the other entity's name in the dataset MIT. Over 90% instances in positive set fit our count. With this assumption, we get entity descriptions from Wikipedia and filter original dataset result. A formal negative instance have a big chance to be credible negative if any of its entities is not mentioned in the description of the other one. If its entities mention each other, then it is treated as unlabeled ones because it is incredible. The description means the text in the Wikipedia pages of that entity. If an entity name refers to multiple entities which have their own pages, all the matched pages are collected together to obtain its description. After dataset construction, we get a labeled set and unlabeled set. Then we use a GAN framework to do relation extraction. The architecture of our semi-distant supervision is shown in the figure. To sufficiently utilize the new dataset, including labeled and unlabeled instances, we proposed a generative adversarial training strategy, which transforms unlabeled instances to labeled data space by generating valid relation representations. We devise a 3-player min-max game to generate valid data distribution with generator, discriminator, and sentence encoder. The generator minimizes the difference of the data distribution of labeled and generative instances, and the discriminator maximizes the probability of distinguishing from each other. Sentence encoder is proposed as the third player, which extracts relation features for all of the instances. We use PCN as our sentence encoder. CN is a widely used structure for extracting features. PCN improves the max polling operation with a piecewise method. The output of convolutional filters are divided into 3 segments by head and tail entities. Therefore, the max polling procedure is performed in 3 segments separately. The pre-trained input embedding includes word embedding and position embedding. The completed training procedure for generative adversarial training is shown in this algorithm. In each iteration, we separately update the discriminator, generator, and the sentence encoder. Here, SI, SG, and SP are all hyperparameters. Discriminator is updated by ascending its stochastic gradient, and the generator and the sentence encoder are updated by descending. To verify the effectiveness of the proposed method, we conduct experiments on a widely used dataset MIT and its new version ANIT. ANIT is a credible dataset filtered by our data construction model. Besides, we apply 16 real-world datasets to further verify the effectiveness of our method on the tasks of segment classification. The dataset details are shown in the table. Firstly, we apply 2 previous methods, PCN and PCN plus ATT on the dataset MIT and ANIT. MIT and ANIT share the same positive instances, where ANIT set has less and credible negative instances. As shown in the figure, methods on ANIT always obtain better performance. The huge gap between PR curves is caused by false negative instances in MIT, which is not used for training and testing in ANIT. We also do manual evaluation at P at the top end. As shown in the table, the huge bias caused by false negative instances on NYT is dramatically alleviated on the dataset ANYT. To further demonstrate the effectiveness of our training strategy, we compare our method with other baselines on the partially labeled dataset ANYT. Our method also gets better performance with the help of unlabeled data. The overall performance of our method compared with baseline for distance supervised relation extraction is shown in the left table. You can see that our semi-distance supervised method achieves much better results than the baselines on all metrics. The huge improvement comes from the accurate dataset and the effective training. To verify the expandability of our method, we conduct additional experiments on the task of sentiment classification. We use LSTM as the sentence encoder. From the table, we can see that LSTM plus GAT achieves better results than the baselines on most of the datasets, also for generating high-quality representations for labeled. In conclusion, we propose a semi-distant supervision approach to solve the problem caused by false negative instances. We first construct a reliable dataset with a knowledge base and additional entity descriptions. With the dataset, we propose a generative adversarial training strategy to deal with plenty of unlabeled instances, which generates valid relation representations. Our experiments show that the proposed approach achieves significant improvement over our baseline. That's all. Thank you.
Questions? Someone needs to ask some questions. We have a lot of papers about this supervision, so the authors can ask questions.
I want to ask how you distribute the module, how to identify the one-to-many relations. I give an example because I have worked in Jiao University and then I worked in Alibaba. So the two triple are also right? So how to handle with the one-to-many relations in your discriminator model?
Our model didn't solve this problem. We just focused on one year.
Did you do that problem in your paper? Okay, so maybe she can give you some suggestions. Any other questions?
Can your method extend to beyond one sentence, like two sentences, or just focus on one sentence and relation?
Are the two mentions always within one sentence, or can they be across sentences?
Just one sentence.
Okay. We have time for one more question. Anyone? So I wonder, when you were looking at the negative false examples, when you try to complete the annotation, so when you say entity description, you're looking at the whole document, like the whole Wikipedia article.
Yeah.
Did you try to look at more fine-grained co-occurrence, for example, whether that entity appears in the same paragraph or same sentence? Would that be a better way to rank the relevance? So now you're checking like whether it's binary, right? Relevance, whether it appears in the article or not, right? So when you validate the pair, you try to check whether one entity appears in the other entity's whole article, right? Did you try to use more fine-grained metric, like check whether they appear in the same sentence or same paragraph? Would that be better than? Okay, yeah, I was just curious. I thought that might give you, more accurate ranking. Yeah. Okay, let's thank the speaker again.